Hi, today I want to give the tiniest introduction to set theory. It's a massive subject, but here's a short introduction to some notation that, especially notation that frequently comes up when talking about sets. So a set is a collection of zero or more objects. Those objects in the set are called elements. Some notation, if you say an X is an element of a set S, then we write X element of S. So what I highlighted in purple there, that symbol is called element of, or sometimes you just call it in, right? X in S, or you could say X is an element of S. They mean the same thing. So that's the basic setup there. What you can do also is specify sets various ways. There are essentially three ways to define a set. There is roster notation. And what roster notation is it means you write your set by just listing out elements between curly braces. List out elements and you separate them with curly braces. So perhaps a very familiar example of something you could write in the roster notation would be something like the set of natural numbers, right? And this would be, right, you list out the elements of the set, you place them between curly braces. There might be infinitely many elements, in which case we put a dot, dot, dot. There might not be infinitely many elements, but this is what roster, in which case you just stop at the other brace, right? But this is what roster notation is. There is also, often we have what's called descriptive notation, which is just what it sounds like. You simply describe what the elements of a set are. So you could say something like, for example, the set in of natural numbers right is the right, and that notation just means the set of natural numbers, right? This is the set of all non-negative whole numbers, right? So there's a perfectly good description of the set of natural numbers, right? It's not very axiomatic or very precise, but it's a description, right? And in certain contexts, that might be a perfectly good definition of the set of natural numbers. Another way that we define sets is by what is called set builder notation. And what set builder notation is you put curly brace, and then you put a variable to represent, or some variable, some expression involving variables to represent what the elements of the set might look like. Right, so that's what lives over here. You start with an expression that shows what the elements might look like, and then you put either a vertical bar, or sometimes people put just a colon, right? Just two dots. You could put either one is fine. I usually go with the vertical bar, but you can do either one. They're both used. And on the other side of that vertical bar is some property, some predicate, right? So some property that must be satisfied in order to be an element of that set, right? By the elements of that set. So that's called set builder notation. Here maybe is an example of how you could write the natural numbers using set builder notation. Suppose we were already given the integers. So, right, this is the set of integers. And then suppose you wanted to use the natural numbers, or use the integers and set builder notation to define the natural numbers. You could do it, right? You could say that the natural numbers, it's consists of what? It's a set of all numbers, right? So I'm just going to call x a number, and x, where does x live? X is being pulled from the integers, but then there's going to, I only want the integers that satisfy certain property. I just want the integers that are greater than or equal to 0. This would be equal to the set of natural numbers. It's a set of all integers that are greater than or equal to 0. That's one way that you could define the naturals. So in set builder, right? So now we're spotting ourselves at integers to then get the naturals, but it's a perfectly good way to write it down. Right? So these are the three main ways that we'll write out sets. We'll either describe them, that's probably the least formal way. Roster notation is often very convenient, especially if you have a finite set. Roster can be very convenient, just a finite set with a small number of elements. You can just list them out, right? And then set builder notation, you specify the type of the element and then some property afterwards, right? And you've probably seen some of these in the in the calculus sequence or in earlier courses. But here we're just kind of getting them down all in one place, being systematic about it. This is the time and the place to do that. So let's then look at operations on sets. So we have several operations on sets. There is the operation called union. And union is written with a giant U, not upside down U, just a U for union. Right, so it's written like that, a big U. And here I'm assuming A and B are sets. So what this is it's the set of all elements X such that X is in A or X is in B. This is the union of two sets. So you may have seen this before. This notation is commonly used, say, in a college algebra or pre-calculus course when you're stating a domain of a function, right? Or say an interval in which a function is increasing or things like that in the calculus sequence. So for example, if you write the function, let's say square root of x squared minus 4, right? Let's consider that function, right? And you want to say, what is its domain over the real numbers? Then, well, what do we need? We need x squared minus 4 to be non-negative, right? And if you want, you could even, let's do this a little more set theoretically than you might do it in, say, college algebra or pre-calc, right? Let's say that the domain is what? Well, the domain is the set of all x in the real numbers such that, that's what the little bar stands for. It stands for such that, or if you put the colon, it stands for such that. So it's a set of all x in the real numbers such that what? Well, if this function is going to be defined over the real numbers, I need the radicand to be non-negative, right? 0 or greater, if I want it to be defined over the real numbers. See, so I just defined the domain in set builder notation, right? Okay. Now, I can rewrite this condition a little bit, right? I can say, hey, this means I need x squared to be greater than or equal to 4, right? Well, how can you square a number and get something greater than or equal to 4? Well, anytime you square a number, it becomes positive, right? So we just need the number to be bigger than 2 or it could be smaller than -2, right? -3, -4, -5, because when we square it, it'll become positive. So there are two ways for this to happen. You could have that x is greater than or equal to 2, or you could have x is less than or equal to -2. Right? These are two ways for this to happen. Well, this is a union. See, it's the set of all elements, right, such that one of two conditions is true, right? See, this is, you could have x be a real number such that x is greater than 2. That's one way that you could be in this set. Union with the set of all x that are less than or equal to -2. Right? And now you can express each of these as an interval, right? We have a way of writing sets that look like this with intervals. So I could say, okay, this is the set of all real numbers greater than or equal to 2. That I can express as an interval. This I can express as an interval, right? It's the set of all real numbers less than or equal to -2. Right? And you leave it written like that, or you could write it instead like this. Right, as a union of those two sets. So this is a very familiar context, doing something very familiar, finding a domain of a function, just like you might in pre-calc or in college algebra, right? But it's doing it in a pretty different notation, right? We're using set builder notation and unions to express these sets. So, and I mean, of course, you could still graph it, right? You could still say that the domain is what we found here, right? It's either 2 and greater, or it's -2 and lower, right? So if you graph this function, essentially this function is, in this region, the function is totally empty. The graph is totally empty, right? The graph would essentially come up this way and come up that way, right? But in between is empty. So, all right. So there we have an example of writing a set in terms of set builder notation using a union, right, to express it. There are other operations, right? Another important operation is called intersection. And for intersection, intersection is, you say A intersect B. And this is written with an upside down version of the union symbol. Right? A intersect B. And what it means is it's a set of all x such that x is in A and x is also in B. And it needs to be in both sets, right? So, for example, I could take A to be the same set that we just had, that interval from -∞ to -2, and B to be the interval from 2 to infinity, right? So the same sets we were dealing with in the previous example. And I could, instead of taking their union like I did up here, I could take their intersection, right? So I could say, I want the intersection. I want the set of all elements that are simultaneously in the first interval and the second interval, right? Well, nothing is simultaneously in the first interval and the second interval, right? So this, you get the empty set, which if you want to put it in descriptive notation, you say just that, the empty set. Or if you want to put it in roster notation, you could just put curly braces with nothing inside. That would be roster notation for the empty set. Or the empty set comes up so often that sometimes we give it its own symbol and people write that circle with a line through it to mean the empty set. They're all commonly used. Just the words, the empty set, descriptive notation, roster notation, curly braces with nothing inside, or circle with a line with a little slash through it. Those are all ways to write, common ways to write the empty set. So this would be an example of an intersection, right? They have an empty intersection because they don't share any elements in common. Or here's another example. Suppose I said on the other hand, suppose I had negative infinity to 2 intersect with 2 to infinity. Right? Well, those intervals do actually have an intersection. They intersect at just 1 point, just 2. Right? And if you have a set containing just 2, that's probably easiest to write in roster notation. It only has 1 element. So just put the curly braces, put a 2 inside, and call it good. Right? So there are 2 examples of intersections, right? One empty, one non-empty. So there we have our first 2 operations with sets, union and intersection. Notice, one thing to notice, the notation for union looks just like a smooth version of logical or, and the notation for intersection looks just like a not pokey version of and, right, of the logical symbol for and. No coincidence, that's by design, right? They are meant to be associated with one another. So then we have complement, so set complement. And what complement is you have to be given a universal set U. So you're usually, from context, it's clear what the universal set U is. So for example, in maybe here where I'm talking about the domain of a function, the universal set is probably the whole real number line, right? That's so we're talking about domain of a function, right? Usually it's kind of clear what the context is, what the universal set would be, but sometimes you really need to specify it, right? So here here for sake of defining a complement, I'm going to specify it. So I'm given a universal set U. Then the complement of A is written, which is written with a overline, right? It's written with a little hat. Is what? It's a set of all X in U such that X is not an element of A. That's what that little slash through the element of symbol means. It means not an element of, right? So it's the negation of being an element. So this is complement, right? So I could, for example, I could say the complement right, the complement of the natural numbers in, say my universe was the integers, then the complement of the natural numbers would be just what? Just the negative integers, right? Because I want everything but the natural numbers. That's what the complement is. So there we have union, intersection, and complement, right? 3 very, very, very common set operations. One thing that I want to show is a really common way to represent sets visually is called a Venn diagram. And what you do is you represent, typically you represent your universal set as a large rectangle. With subsets inside represented as circles. And this is frequently a handy visual representation of sets. And then elements of sets are shown inside those circles. So, for example, here would be a Venn diagram depicting what we just observed, the universal set of integers And then in here, whoa, in here, I could show the set of natural numbers as a circle, right? So here I would have 0, 1, 2, 3, etc. inside the natural numbers. And then out here in, see, this is in complement is what's outside, right? And maybe let me actually show this with some color. Right, so in complement, that's all this stuff. That's anything I write outside of that circle, right? It is anything that's in the universal set, but not in N. So what would be out here? I'd have -1, -2, -3, and so on. So it's a nice, often a nice visual representation. And it doesn't matter spatially where you put them in that region, just that it inside the circle means an element of the set, outside the circle means not an element of that set. It gets even, let's say, more handy when you have multiple subsets. For example, if you had A and B subsets of some universal set U, right? You could draw it like this, where you draw A and B. And then what you could do is you could actually use this to have visual representations of different sets, different combinations of sets. For example, if I asked you where is A intersect B in this diagram, it would be exactly this little lens there in the middle, right? If I asked you, oh, sorry, intersect. I said intersect when I wrote union. Intersect. There we go. There we go. If a red flag went off at that moment, good. So, and you know, I could do. Here will be Colorado about it. I could do A union B. What would A union B look like? So A union B, that would be the two sets all together, right? So this would be including the middle, right? So A union B would include all of that, right? So you can sometimes use a Venn diagram as a quick visual representation. It's very handy, right? It also lets you, if you want, you can also do a quick visual argument to prove equivalence between different types of sets. So for example, we could use a Venn diagram to find a simpler way to write the, how about this? Let's write the complement of A intersect, let's say union, A union B complement. Say we have this, right? So I want to find a simpler way to write A, the complement of A union B complement. So what could I do? Well, I could take my Venn diagram and I could say, okay, what do I want to do? I want to take together the set B complement, right? So here's A and B. So B complement, what is B? What's in B complement? Let's shade B complement. So B complement is everything outside of B, right? So there is, right, that would be B complement. Is shown in green, right? So it's everything outside of B, including the part of A that is not in B. Then what else do I want? I want to look at A, right? Here's the set A. So I did, we did B complement, right? Now I want A. And A is all of this stuff. And now I want to take their union, right? I want to calculate this union. So what is the union? The union is going to be all of those elements all lumped together, right? So anything that's in either region, anything that's purple or green or both, anything shaded like that counts as part of the union. So the union there is going to be what? It's going to be all of the green, right, along with all of the purple, right, taken all together, right? That's the union of those two sets, right? But now I want the complement of the union. So now I want everything that's not red. That's what the top is, what this complement is saying, right? Is saying give me all the not red regions. So what are all the not red regions? Well, if you look, it's kind of just the part of B that is outside of A. That's really all that it is. It's just this little moon, this little nearly full moon looking thing centered at B, right? It's that white region. So what we could say at the end of this, and I'm gonna, this diagram now is getting pretty gross, right? So I'm gonna say thus, this set is what? It's really just this region right here. Right? It's just it's just all the stuff that's in B, but not in A. That's a much simpler way to write this. So I could say this is the set of all elements of B that are not in A. Right? So there it is in set builder notation, or I could just write it in descriptive notation. Right? This is the set of all elements of B that are not in A. Right? Okay. Well, I claim this gives us another way to write this. Another way to say this, I need both of these properties to be true. I need X to be an element of B, and I need X to be not in A, right? You could think of X as anything from the universal set, but where X is in B and X is not in A, right? Okay. I have an and in a set builder notation. So how could I express this? Well, as an intersection, right? So I could say this is the set of all X that are in B intersected with the set of all X that are not in A. But I actually have names for all of these now, right? I have names for all of these sets. The set of all X such that X is in B. Well, that's just B, right? The first set is literally B, the set of all elements of X that are in B. Let's just said the same thing twice, right? Now the second set is the set of all elements that are not in A. We have a name for that. That's called A complement. So there we go. We just found a much simplified version of what we had up there. The complement of A union B complement, that's a lot more cleanly expressed as B intersect A complement. Or if you want to be, alphabetical about it, we can write it as A complement intersect B. Right? So that is a nice simplification that we were able to do there. What just happened here? This is, in reality, a version of De Morgan's law. This is a set theory version of De Morgan's law, right? There's De Morgan's law in logic. There's De Morgan's law in set theory. If you look at what happened, you can look at this in terms of the Venn diagram, but you can also look at it in terms of De Morgan's law. De Morgan's law for sets says that if you want to take the complement of an intersection, you can, right? You distribute the complement onto the sets if you flip the intersection to a union. Also, if you have a union and you want to take the complement, you can flip the union to an intersection and take the complement of each set, right? This is De Morgan's law for sets. Very similar to De Morgan's law, say for quantified statements, right? For and or, right? Flip the there exists to a for all, or flip the for all to a there exists as you pull the not in or out, or flip the and to an or the or to an and as you pull the not in or out. Same thing here. Flip the intersection to the union or the union to the intersection as you pull the complement in or out. Same process, slightly different operation, right? So if you want, then you could look again, instead of using a Venn diagram, another way to simplify this expression, you could simplify it using De Morgan's law, right? How could I simplify this using De Morgan's law? Well, De Morgan's law tells me to flip the union to an intersection as I distribute the complement. But one of these sets already had a complement on it, right? And the complement of a complement is just the original set, right? Because I'm saying the complement of B, or all the elements that are not in B, right? So if you want all the elements that are not in the complement of B, that's just B. It's a double negative, right? If you say it wasn't true that I wasn't there, then you were there, right? It's a double negation, and it reverts back to the positive. So this is our this is another way to do that same simplification, right? But here we used De Morgan's law instead of the Venn diagram. Both totally valid ways to look at the simplification, right? Pretty different, right? One is sort of very visual. The other one is more formulaic, right? They're both totally valid. So, all right, there we go. So there's a little intro to some of the fundamental ways to represent sets, to work with sets, some of the fundamental notation and ideas surrounding sets. Great, thank you.